Welcome to the deep dive. Today, we're plunging into one of those really essential but often unseen bits of technology in modern manufacturing: wire electrical discharge machining. You'll mostly hear it called wire EDM. Yeah, and when you think about what goes into making, say, high performance stamping molds, the kind that make parts for, well, almost everything these days, phones, cars, you name it, you're dealing with unbelievably tough stuff, hardened tool steels, super intricate designs, and the stakes are high. A tiny mistake, hugely expensive. It's a field where precision isn't just nice to have, it's everything. So for the people making these molds, the real puzzle is how do you make them tough, accurate, and economical, especially when the old ways, traditional machining, just aren't up to scratch. Our deep dive today is really about why wire EDM isn't just a good option, but often the only way to tackle these really demanding jobs. We're hoping to uncover some pretty surprising things about how it works.
Right. And our mission, really, for you listening, is to get a real feel for the specific problems Wire EDM solves that, honestly, other methods just can't handle. We'll dig into the engineering, why it's so vital for creating those super strong, monolithic, one-piece dies that form the backbone of so many products we use.
Okay, let's get into it then. Anyone who's worked in mold making has probably felt that horrible sinking feeling. You've poured days into a mold, it goes for heat treatment, which is critical, and then
Yeah.
crack.
Oh, yeah.
Or maybe worse, it breaks on the first production run, wipes out weeks of effort, material. It feels like bad luck, but often it's hidden stress, right, from the machining done before hardening. So how does wire EDM avoid that nightmare?
Well, the really game-changing thing about Wire EDM is that it's non-contact.
Yeah.
It's thermoelectric. The wire, it never actually touches the steel.
No physical contact.
Exactly. Instead, you have these incredibly rapid electrical sparks, like tiny lightning bolts jumping across a very small, very controlled gap. They're incredibly hot. We're talking over 8,000 degrees Celsius. And each spark vaporizes a microscopic particle of the steel. Then, the dielectric fluid, this special insulating oil or deionized water it's all submerged in, instantly quenches that tiny spot, cools it super fast, and flushes away the vaporized metal debris. Clears the path for the very next spark thousands of times a second. And the crucial point, the absolute key takeaway here, is this means zero mechanical stress gets put into the material. No pushing, no pulling, no friction.
Right, no force.
None. Which completely eliminates the main cause of those microcracks you worry about, especially in super hard, brittle steels. Things like SKD11 hardened up to HRC 60 or even more. That stuff is incredibly hard, but it doesn't like stress.
And conventional milling, that's all about force, isn't it?
Absolutely. Huge mechanical forces, which inevitably creates stress points. Wire EDM just doesn't. It sidesteps that whole problem.
That's really clever. Kind of like sculpting with lightning, not a chisel. But okay, vaporizing metal at 8,000 degrees, does that affect the surface that's left behind? Does it create its own problems, like a burnt layer or something?
That's a really good question. And yes, there's a nuance there. That initial high-energy cut, the roughing cut, does leave a very thin layer on the surface. It's called the recast layer. It's hard, formed precisely, but it can be a little brittle.
Ah, okay.
But that's where the strategy comes in. That's why we use skim cuts. After the rough cut, we do multiple follow-up passes, each one using progressively lower electrical energy.
Lower energy skim cuts, got it.
Each skim cut basically removes the compromised recast layer left by the previous pass. So you're shaving off that brittle layer, leaving behind a cleaner, metallurgically sound surface each time. The final surface, it's free of that tensile stress, free of micro cracks. And that's absolutely vital for the mold's lifespan, preventing fatigue failure down the road. It's a neat solution, really.
It sounds incredibly elegant. So, okay, the stress problem is solved, brilliant. But what about the shapes themselves? These molds often have incredibly sharp inside corners, delicate little features, things that a round milling cutter just physically can't make, right?
Exactly. And that's another area where Wire EDM just excels. The tool isn't a rotating cutter. It's this thin wire, sometimes as thin as 0.1 millimeters.
Tiny.
Really tiny. And it's constantly being fed from spools, so the cutting edge is always brand new, always perfect. You don't have the tool wear issues you constantly fight with in milling. And that super thin wire lets us achieve what we often call virtually sharp internal corners. If you're using a 0.1 millimeter wire, you get an internal corner radius down to maybe 0.075 millimeters. That's the wire radius plus the tiny spark gap.
0.075 millimeters, that's practically nothing.
It's incredibly sharp. something no milling cutter could ever hope to achieve because it's always limited by its own radius. And again,
Yeah.
because it's non-contact, there's no force pushing on the part.
Yeah.
So you can machine features that are incredibly delicate, super thin walls, tiny little ribs without any risk of bending them or breaking them off.
Makes sense.
The ultimate demo of this, I always think, is cutting a matched punch and die from one single block of steel.
From one piece, how does that work?
You program a single cut path, but with a very slight taper angle. The machine cuts through, and the inner piece, the slug that falls out, that's your punch. The outer piece is the die. And because of that controlled taper and the precision of the cut, they fit together perfectly with a uniform clearance measured in microns right off the machine. Pretty amazing to see.
That is amazing. One cut, two perfectly mating parts. It really highlights the precision aspect. And in stamping, like you said, that punch die clearance is critical. A few microns off and you get burrs on your parts. Tools wear out fast. Production stops. So what are we talking about in terms of actual numbers? What precision, what tolerances can Wire EDM realistically hit? Is there a trade-off?
Oh, the precision is definitely impressive. We can reliably achieve dimensional accuracy down to plus or minus 0.002 millimeters. That's 2 microns.
2 microns. Okay.
And the surface finish can get smoother than wrap 0.4 micrometers. Wrap is roughness average. It's how we measure texture.
Yeah.
And 0.4 is exceptionally smooth. It's almost mirror-like, but it has this non-directional matte texture, which is actually great for holding lubricant on a working die surface.
Oh.
So yeah, we're operating at the micron level. Now, the trade-off you asked about, it's essentially time. Achieving that micron-level precision comes down to the machining strategy specifically, how many of those skim passes you perform after the initial rough cut.
Right. The skim cuts again.
Exactly. A single rough cut might get you within, say, plus or minus 0.025 millimeters. Pretty good, fine for some general shapes. But to really tighten that tolerance and improve the surface finish, you add skim passes. Each pass uses lower energy, removing just tiny amounts of material, refining the dimensions, smoothing the surface. You can literally dial in the required precision and finish by adding passes. So for example, a standard part needing maybe big 0.01 millimeter, that might take 2 passes total, the rough plus 1 skim. Roughly doubles the machining time compared to just roughing.
Okay, makes sense.
But if you need a high precision punch, maybe aiming for 0.005 millimeter tolerance and that nice 0.2 to 0.4 ray finish, you're probably looking at 3, maybe 4 passes. And yeah, that might take, say, 3.5 times longer than the rough cut alone.
More passes, more time, tighter tolerance.
Precisely. And then for the really critical stuff, medical implants, aerospace parts, optical molds where you need tolerances like 0.0001 to 0.0025 millimeters, and a surface finish maybe under 0.2 ray, you could be doing 5, 6, even more passes. The time goes up significantly, 5 times or more relative to roughing. It's a direct relationship.
Time invested equals precision achieved.
That's a very clear trade-off. So thinking about a manufacturer, maybe they've got both Wire EDM machines and high-speed CNC milling centers in their shop. How do they decide which process to use when? Is it one or the other, or do they work together?
That's a great practical question, and the answer is it's almost never purely either. The smartest, most efficient approach, especially for complex tooling, is usually a hybrid approach. You leverage the best of both technology.
A hybrid approach. The number one deciding factor. It usually comes down to material hardness.
Ah, back to the hardness.
Yep. Wire EDM simply doesn't care how hard the material is. Soft steel, fully hardened tool steel, about 5860 HRC.
Yeah.
It cuts them all the same way. So for machining after heat treatment, EDM is often the only practical choice. High-speed milling, on the other hand, really struggles with very hard materials. Economically, it's usually limited to steels below about 58 HRC. Trying to mill harder stuff is super slow, it chews through expensive cutting tools like crazy, and you still risk inducing stress.
So milling happens before heat treatment, EDM happens after, generally speaking.
That's the general rule, yeah. Then there's geometric complexity.
Right, the shapes they can make.
Milling is fantastic for complex 3D surfaces, curves, contours, and importantly for blind features. Pockets or cavities that don't go all the way through the part.
Because the cutter comes down from the top.
Exactly. Wire EDM, remember, needs that wire to pass all the way through the material. It can't easily do blind pockets. But where EDM wins, geometrically, is those super sharp internal corners, radii under 0.5 millimeter, where milling cutters can't reach, and also for deep, very narrow slots or channels. The thin wire is perfect for that.
Okay, so different strengths for different shapes.
Right. So the most efficient strategy, the hybrid approach, often looks like this. Use the high-speed mill first, while the steel is still relatively soft. Quickly machine out the basic overall shape, maybe any 3D contours, rough out big cavities, get the bulk removal done fast.
Makes sense. Use the speed of milling.
Then You send the part for heat treatment to get it hardened. After it comes back, hard and stable, you take it to the Wire EDM. And that's where you cut the final precise profiles, the critical holes or apertures, and especially those sharp internal corners that define the actual working edges of the tool.
Best of both worlds. Speed for roughing, precision, and hard material capability for finishing.
It's exactly. You get the speed and 3D capability of milling, combined with the incredible accuracy, sharp corner capability, and stress-free cutting of Wire EDM on the hardened material. It's a really powerful combination. So just to quickly recap that comparison for you, hardness limit. EDM doesn't care. Milling is best below 58 HRC, minimum internal radius. Under zero point 0.1 millimeter for EDM, over 0.5 millimeters typically for milling, tolerance. EDM routinely hits 90 metal 0.005 millimeters, even down to 90 made 0.001 millimeters. Milling is more like made 0.025 millimeter, typically material removal. Milling is much faster. Blind features. Milling, yes. EDM, no. Stress. EDM is just localized thermal. Milling is mechanical and thermal. They really complement each other.
That's a fantastic summary. It really paints a clear picture. So bringing this all home, it seems pretty clear that Wire EDM, with its unique knack for cutting super hard steel without stress and its amazing precision for those complex, tiny features, it really is fundamental, isn't it? For making the durable, high-performance stamping molds that, well, basically build our modern world, a real hidden workhorse.
It truly is. And maybe here's a final thought for you listening. Next time you pick up your phone, or get in your car, or even just use a kitchen utensil, take a second to think about the unseen precision that went into making it. That micron-level accuracy achieved through processes like Wire EDM and those clever hybrid strategies we talked about is directly linked to the quality, the durability, maybe even the affordability of so many things we take for granted. Appreciating these specialized techniques, I think, really uncovers this fascinating hidden layer of science, engineering, and sheer craftsmanship that exists all around us, often in the most ordinary objects.